Okay, so thank you everybody for this coming to this session of the discrete optimization talks. Our first speaker is going to be Claudia D'Ambrosio. She's a senior researcher in CNRS and a professor in the École Polytechnique, and her research is mostly focused on theoretical and computational aspects of mixed integer nonlinear programming. She has received several awards during her professional career, including a Euro Doctoral Dissertation Award, and also was nominated to the CNRS Bronze Medal in 2018. So thank you very much, Claudia, for being here. We're happy to hear about your research.
Thank you very much, Margarita, and thank you, Alex and Silvia as well for the invitation. I'm really glad to be here. So today I'm going to speak about work where I compare strong formulations for piecewise convex functions. So, okay. So I will introduce some motivation and then focus on two kind of formulations, and then summarize some previous theoretical results, and then move to the new contribution, and then conclude and briefly summarize what we are currently working on. And this is a work with Antonio Frangioni, Claudio Gentile, and Renan Sperse and Trinidade. Okay. So when I speak about piecewise convex function, I speak function of this kind. So like we have a univariate function, so I will stick with univariate for today. The x domain can be divided into intervals in which the function is convex. So for example, here you can see that we can see two intervals of x, one in the x-axis where here the function is convex, and in that other part, the function is linear, thus convex as well. And so the full function is not convex, but it's piecewise convex. This is the definition that I will use for piecewise convex function, and it's a generalization of a classic definition of piecewise linear functions that are known and studied into the literature. Okay, so in this talk, we will introduce and compare different formulations that are strengthened with perspective functions for this kind of, for integrating this kind of function in mathematical optimization models. Okay, so first of all, one of the classic papers in which comparison between piecewise linear function formulations is introduced is this paper that I cite here by Croxton and co-authors dated 2003. So there are several potential formulations of this. I will mention convex combination formulation, multiple choice, and incremental formulation. Today, I'm going to focus on the last two because we know from previous results that convex combination is equivalent to multiple choice in the case of piecewise linear and convex functions. So I will start from a multiple choice formulation, and I will introduce a general formulation that is valid both for the piecewise linear function and for the piecewise convex. Okay, and to do so, I will, to introduce the formulation, I will start with a function. So I will stick with linear just for simplicity of a presentation, but you will see that the formulation will be valid for a piecewise convex as well. So here, as in the previous case, we have an x, that is our variable, and f of x is the function that we want to model within a mathematical optimization problem. And so we have four pieces here that are represented by each of these segments that compose the function itself. So the input that we have are the values of the x at each of the extremes of the segment. So you can see here that we have 4 segments and 5 of such points. The first point is typically the lower bound, and the last point is typically the upper bound of the variable. And then we have other intermediate points that are 3 in this case. We will call these points breakpoints. And we also know the value of the function at these points. So f of L1 up to f of L5. So while the x coordinate is in increasing order, the value of f can be in whatever order actually. So you can see, for example, that f of L5 is lower than f of L4. Okay, so this is our input, and actually we suppose that our function is continuous. So let's now introduce some variables. So besides x, we also have four other x's that we call x1, x2, x3, x4, which correspond each of them to one of the segments that we have, so to one of the pieces. And x will be just the sum of these 4 variables, which are continuous. And now to model the pieces, we introduce 4 binary variables, y1 to y4, and they have to sum up to 1. And in particular, the interpretation of the value of the binary variable is that we kind of select one of the pieces, in particular the one that include the value that is taking the variable x. So we will see a numerical example in a few seconds. And let me now introduce the other constraints. So for each of the pieces, so for I from 1 to 4, we define that xi is linked to y, so that it is equal to 0 whenever yi is equal to 0. And it's defined between, it takes a value between li and li plus 1 whenever y1i is 1. So for example, so we will see an example in 1 second. And now we are left with the modeling of the function itself. And in particular, we see that the function, and this is the part that is different with respect to the piecewise linear, because we have to deal with convex functions. Then we have the value of f at 0, plus for each of the segments, we have the value of f at xi minus f0. Why this complicated formula? So it will be clear in 1 second when I will show you an example. So suppose, for example, that in a solution x, in an optimal solution or a feasible solution, whatever, x take the value 5 here, okay? Then it means that it falls into the 3rd segment. So the corresponding values of all these variables will be y1 will be equal to 0, y2 will be equal to 0, y3 equal to 1, because actually the value of x lies between L3 and L4. And y4 will be equal to 0. So now let's see the value of the x's. So thanks to these constraints, we know that x1, x2, and x4 will be equal to 0. And x3 will be equal to 5. Okay, because the value of x will be given by the unique xi that is not taking the value 0. Now, let's have a look at the formula providing the value of the function at 5. So we have f0 here plus a term for each of the summation, and we know that for I equal to 1, 2, and 4, xi is equal to 0. So we have f0 minus f0, f0 minus f0, and f0 minus f0. And only for I equal to 3, xi, it takes the value 5. And so everything so cancels out besides this term that is fx3, which is exactly f of 5, which is the value that we want. Okay, so now in the most generic form, actually we can say that x is equal to the sum of xs, where s is the index of the pieces. And then we have the binary variable cardinality of s binary variables, and they have to sum up to 1. So this is exactly the constraint that we had before, but for a generic number of intervals. And then we have the value of f provided by this more generic constraint. Okay, now what about, so I was mentioning the perspective function. So this is the standard formulation generalized to the case of convex function. In the case of, in the linear case, it can be simplified, but we are interested in the general case in which we can also deal with piecewise convex functions. And now we want to apply perspective reformulation in order to strengthen this formulation and have a better continuous relaxation of this problem. And in particular, so I will have just one slide on perspective function and reformulations. So we suppose we have so here I have a different notation just because it's like independent slide, let's say. Suppose that we have a convex function h of x. We define its perspective function as the function obtained like this, where y is a binary variable. So we pre-multiply h by y, and then we divide x by, so the argument of h by y. And we know that when this function is restricted to this mixed integer set that you see here, composed of x and y, where x is equal to 0 when y is equal to 0, and x can take any value between 0 and u whenever y is equal to 1, then the perspective function represent its the convex envelope. And so we're interested in this because by applying so replacing the convex function by its perspective function, we can tighten the lower bound of the continuous relaxation in the case of minimization problems. And so we are going to do, so this is just a graphical representation in which we have the point 0, 0, 0, where for the case of the binary equal to 0, and then we have a convex function for the case of y equal to 1. Okay, now what do? We just apply the perspective reformulation to the convex function that we have. So note that we have everything is linear. So this constraint is linear, this is linear, this is linear. The only convex one is this. And so for each of these term in the summation, we apply the perspective reformulation by multiplying the function itself by the binary variable and dividing x by the binary variable. And so we are going to consider only the perspective reformulation of the function of the formulation that I showed you. Okay, so if there are any questions specific on this, I will take them. Because then, yes.
Yeah, sorry. Hi, Claudia. Actually, I have a question because
Yes.
y is a binary variable,
Yes.
0 or 1. So wouldn't it be like not well defined having x divided by y?
That's a great question. Thank you for the question. So I take the chance to say that actually when trying to solve this formulation, what we are going to do is to just relax the constraint that is convex that contains the perspective function and generate cuts over that. And so we will add the cuts only when they are well defined.
Okay, thank you.
Thank you. Okay, so if there are no more questions, then I will move to the next formulation, which is the incremental formulation. So it's an alternative to the multiple choice or convex combination that I will not present today, but the setting is the same. So we have a function, the same function as before, 4 segments, 5 breakpoints, and we have the value of the function at these points that we're going to use. And so we have, I will use a similar notation, but the meaning will be different. So in particular, x, so we will have a continuous variable for each of the segments here, but instead of taking values like either 0 or between the L1 and L2, for example, x1 will take a value between 0 and this difference, which only provides the length of the segment. So for example, x1 will take a value between 0 and 2, which is the length of this segment. x2 will take a value between 0 and 1, which is the length of the second segment, and so on. And actually, x will take the value of the lower bound, so L1 is its lower bound, plus the sum of each of these variables. And actually, more than one of these variables can take a value that is non-zero, and they will compose in some sense incrementally the value of x. That's why it's called incremental formulation. So also in this case, we have binary variables, one for each of the segments, but more of one of the integer of the binaries can take a value 1. And in particular, so I have here the formula, so the constraint that links the x and the y, and for each of the segments, I have that xi will be equal to 0 when yi is equal to 0, because the upper bound will become 0, and it will force as well yi plus 1 to be equal to 0. And when yi plus 1 is equal to 1, it means that actually xi will be forced to take its upper bound, and thus yi will take value 1 as well. So the only case in which xi will take a value that is neither its lower bound nor its upper bound, it's the case in which yi is equal to 1 and yi plus 1 is equal to 0. And then we now have slightly different definition of the function which is given by f at its lower bound plus the sum over all the segments of f li plus li xi minus f of li. So we will see that almost all these terms will cancel out as in the first case, but let's see the case of x equal to 5 and what value will take the variables. So in this case, actually, in order to get an x that is equal to 5, we need to start from L1, which is equal to 1, plus incrementally use the first segment, the second segment, and part of the third segment. What does it mean? It means that the binary variables of all the segments up to the segment where the value of x is will take a value 1, and the rest of the binaries will take a value 0. So why is this? Because actually here I tried to highlight it with colors. So we have that x1 is equal to 2, which is exactly the length of the interval. So we take all the contribution from the first interval. For x2, we take the full contribution for the second interval, that is 1. And from the third one, we take only 1 unit. And so if we sum up, so we have 1, which is the value of L1, plus 2, plus 1, plus 1, plus 0, and it sums up to 5. And so this is the reason why there is this value of the binaries. So the binaries activate all the segments that contributes to the value of x, basically. And so now concerning the value of f, so we have that this is f1 plus f3 minus f1, because x 1 plus 2 in the first case minus L1 is equal to minus 1, and so on for each of them. And you see that they all cancel. So this cancel out with this cancel out with this with this with this, and we are end with f of phi, which is exactly what we want as a value of our f. So this is an alternative formulation, and we have that these are the constraints. So the most generic formulation, just the constraints are the same ones, but for a most generic number of pieces. And you see that also in this case, we have everything that is linear besides this part here, which is convex, and we can strengthen it with the perspective reformulation. And in practice, what will happen is, again, also in this case, the fact that we will use a cut-in-plane method to solve this problem. Okay, now that I introduced this, I will move to the theoretical results. So in the paper that I was mentioning before by Croxton and co-authors, they proved that in the continuous relaxation of the three formulations are equivalent for the piecewise linear case. Okay, so they just focus on the piecewise linear cases. So what we wanted to explore is what happens if we move to the generalization to the piecewise convex case. Are they still equivalent? So our starting point was a theorem by a result actually by Frangioni et al., a paper from 2020. There was a corollary there where they said that they could prove that the multiple choice formulation, so the first that I presented, constraint, describe the convex envelope of each piecewise convex function. So there is no doubt that we cannot do better than a multiple choice formulation, but the question now is incremental as strong as multiple choice formulation? So for a long time, our conjecture was that also in the general piecewise convex case, it was the case, but actually we could prove that this is not the case. So the multiple choice formulation is stronger than the incremental one. So the proof is pretty simple. So we just identified a numerical case in which the continuous relaxation provide a worse lower bound than the one of the multiple choice. And in particular, we show you graphically. So we have the case in which we want to minimize a function that is piecewise defined as this. So we have with x between 0 and pi is minus sign of x, and for the rest is 0. So it's what you see here. Okay. So the red part that you see here is the value of the function of the continuous relaxation of the multiple choice, and on the contrary, the blue one is what is provided by the incremental formulation. So you see that it's larger and it doesn't identify the convex envelope. But if we consider, on the contrary, this function where we have 0 first and then sine of x, then the two coincides. So just to, I do not have much time, but I will just tell you about the proposition that we have is that if the piecewise convex function that we have we are trying to formulate two pieces, and in the first piece it is linear, and in the second one it is convex, then the continuous relaxation of MC and incremental are equivalent. So this is exactly the case that you see here. There is no difference. But in general, MC is better than the incremental case. We do not have the time for the sketch of proof, but it's pretty standard. And so I will now conclude by telling you what we are working on right now. So we identified this, like in general, we identified, we proved that the formulation, the generalization perspectivized of piecewise convex functions formulation, they are not equivalent in general, but we identified a specific case in which they are. And so we are wondering if we can find other specific cases in which the continuous relaxation are equivalent. The other thing we are working on is, like, we stick with the univariate function here. We want to see what happens if we go to higher dimension or to other classes of problems. In particular, we're working on bivariate functions right now. And we are interested into strong formulation for piecewise polynomial functions in general that can be very useful in many applications. And I thank you for your attention.
Thank you so much, Claudia. Are there any questions? I noticed that there's one in the chat, in case the person that put it there wants to read it out loud. Okay, otherwise
oh, yeah, okay,
I
we're
can
good. You
read
want to read it?
Yeah, I can read it, don't worry. So the question was, do we need the extra constraint that y subscript cardinality of s plus 1 is equal to 0 in the incremental formulation?
So that y, oops.
Yeah, so we for the last, so if we need the y equal to 0 for the last
yes. For the last one, yes, we can have that the last one is equal to 0. Yes, true.
Okay, great. Thank you. And Alex also have a...
Well, I see Robert. I don't know if he wanted to ask a question because he went on video. Maybe he can go first.
I was going to ask these like logarithmic piecewise linear formulations where you have many fewer binary variables.
Yes.
Did you think about applying these ideas to those formulations?
That's an interesting question. Yeah, no, like we didn't try it. I think it will be a good let's say mixture of like strong formulation plus less binary variable. I think it's a good idea. It will be a good idea. It's not so straightforward, I will say, to apply this, because then when in the perspective formulation, then it might be that there is not only one binary variable that activate and deactivate here, so it's not straightforward. That's why we didn't do it, but I think it will be interesting to explore.
So I have what's hopefully a quick question. So you have this result that the multiple choice formulation is better than the incremental when the order of the pieces is switched, basically. And this is for two pieces, I guess. Do you have like an approximation? Like, is there like a bound? Like the multiple choice incremental is like within a certain factor of the multiple choice, or it's arbitrarily worse as a function of the number of pieces? And like, it seems like the ordering of the pieces is also kind of like, is there like a way to reorder the function in some way to make the incremental formulation better?
These are all interesting questions. I do not have an answer, but I think so. The order is important. We didn't really check what happens for more than two pieces. To be honest, we identified this from actually we started with a computational comparison, and then we find out the theoretical results, because at the beginning we only had equivalent. And it was because all of the instances that we were initially testing were like of this form here, but then when we enlarged our test bed, then we found out that it was not the case, and that we were thinking it was a bug, but then we found the result. But I think, yeah, like right now where I'm studying with some students, some piecewise convex functions for applications in neural networks. And in that case, there are 3 pieces. So maybe next, in a future talk, I will tell you more about
Got
this.
it. I look forward to it. Thank you. So maybe let's thank Claudia one more time.
Thank you.
And we'll move on to our next speaker.